Hi, and welcome to Failurology, a podcast about engineering failures. I'm your host, Nicole.
And I'm Brian, and we're both from Calgary, Alberta, Canada.
Thanks again to our Patreon subscribers. As always, we really appreciate your support.
For less than the cost of a cup of coffee in Canada and likely the United States, you can hear us talk about more interesting engineering failures.
That's $5 a month to get twice as many episodes, some more train tangents, twice as many failures. Please go check it out. And that's $5 now, and it's going to stay $5. Our Patreon is inflation proof. This week in engineering news, counterfeit part detection. Researchers at Texas A&M University developed a method to imprint a magnetic tag within manufactured hardware during fabrication. The tag is hidden and it contains authentication information. And they're also more permanent and unique than barcodes or QR codes or something else that's added onto the part after fabrication. As the US invests billions of dollars in manufacturing, ensuring the security and reliable authentication is a pretty big concern to make sure that you're getting what you are paying for or what you think you're getting. Nowadays, someone can copy and fabricate cheaper alternatives to your designs. We're looking at you, Amazon. Sometimes passing them off as their own at a lower price and lower quality. So these tags aim to stop that or at least make it more difficult. Competition to an extent is good, but if months after you make a product and put it out there on the market, especially when it's something you've worked really, really hard to develop, and then immediately a knockoff version comes out, I mean, that would kind of suck. And that would definitely deter me from developing new products. So, while competition as a concept is good and it does help keep prices down for people that are inventing new products, it's nice to be able to have some type of way to track whether or not they're authentic. And this magnetic tag strives to do that, which is pretty cool.
Previous methods for imprinting information are expensive and require specialized tools, which creates a barrier for use. This most recent study at Texas A&M is the first to use magnetic properties of the material to imprint information on a non-magnetic part, which sounds pretty cool. The method of reading the tags is still being optimized to be more secure, even looking at potential dual authentication. So if you want to read more about this study, check out the link on the webpage for this episode at failurology.ca.
Before we move on, Brian, have you seen those videos where parcels or other things go down that conveyor belt, and depending on what the sensors sense, it kicks them onto different other conveyors?
I have seen those videos. Where I went to school here in Calgary, they had a manufacturing engineering program as well. It was part of the mechanical department. And some of my friends that went through manufacturing engineering actually wound up working on, I don't know specifically those systems, but very similar systems that would parse different parts and materials onto different conveyor belts or different boxes, different areas of the factory. So I've always thought it was really neat. I've spent far too much of my time playing Factorio over the last 5 or 6 years. It's essentially a game that is all about building a giant factory for things. So I've spent a lot of time doing the conveyor belts and the loading thing. But I think those videos are really cool.
So this product isn't necessarily tied to that technology. That's what was in my head as I was reading about this magnetic tag that's affixed to different products during manufacturing. They're not related. You can have one without the other, but that was what I was visualizing. I thought that was interesting. And if you haven't seen those, check those videos out.
This week's episode of Failurology is brought to you by the Sit Down Stand Up Paddleboard Company.
Whether you like to sit down or stand up,
the Sit Down Stand Up Paddleboard Company has something for you.
Don't miss our paddle sale. It's quite the ordeal. Now on to this week's engineering failure, the Tacoma Narrows Bridge, also known as Galloping Gertie. We don't normally do two similar failures back to back, or at least we try our best not to. I think it's really important that we talk about engineering failures from a bunch of different disciplines and different parts of the world. I think it gives a really good representation of the engineering profession as a whole. I know that sounds weird to use failure to talk about our profession, but like they say, failure is integral to engineering. So I think it's important. And it also keeps things interesting. But today we're making an exception. So the last episode, we talked about the Golden Gate Bridge. Leon Mossieff, who designed the Golden Gate Bridge's basic structural design, and he used his deflection theory to design a thin, flexible roadway that flexed in the wind. He also designed the Tacoma Narrows Bridge, and it opened 3 years after the Golden Gate on July 1st, 1940.
So not only is this a back-to-back bridge episode, this is a back-to-back with the same designers of both bridges.
Yes, and the Golden Gate is in Northern California. Tacoma Narrows Bridge is in Washington State, so they're both on the Pacific coast, exposed to pretty similar climates, and they're only about 1,200 kilometers apart. So I think there's a lot of things that link these two bridges together. Except, while the Golden Gate Bridge is still standing 86 years later, the Tacoma Narrows Bridge collapsed on November 7th, 1940. Yes, the same year it opened. It was a little more than 3 months old at the time. So it did not fare well. The Tacoma Narrows is also a really popular failure. It's one that's been on our list since the beginning. It's talked about a lot, probably significantly more than if it would have been still standing today. And I have to admit, I'm always a little nervous to talk about the ones that are really popular because a lot of people have heard that story and a lot of people, have formulated their own opinions. There's been lots of people that have looked at this bridge and discussed it and, reverse engineered it and so on and so forth. So I'm always a little nervous to do these failures. I always hope that we're bringing something interesting to the table. And so while we're doing something that's been talked about, hopefully our spin and our perspective on the bridge will be interesting. The bridge has also actually been rebuilt twice, which we're going to get into shortly. And while it did collapse, as with any good catastrophic failure, it taught us a lot of things about structural engineering and bridge building throughout the US and around the world.
Yeah, I like to think in the kind of in the early 20th century, so kind of from 1900 till I'm going to say 1960, there were such major advances in materials technology and in design methods that as engineers we were all learning, or back then engineers were kind of learning about what worked and what didn't work. Like there was no computer modeling, there was no finite element analysis, there was no kind of technology that we take for granted to do things like stress analysis on building design today. That didn't really exist back then, or if it did, it was very rudimentary and it likely had to be done on a slide rule. So a lot of the things that we've learned along the way unfortunately did come out of failures, and unfortunately a lot of people did wind up losing their lives to a lot of the time something that in today's society or in today's engineering it would be immediately recognizable, but back then they just didn't have the technology or the knowledge or skill base to know any better.
Yeah, and to add on to that, the wind played a big factor in this collapse, and that was just something that was not well understood in the 1930s and 40s when this bridge was built. So not only has bridge building and structural engineering itself come a long way, but also the different loads and factors that can impact the bridge over time has also come a really long way.
And we just, especially on the wind side of things, we just have so much better data now because we have so many more sensors that are collecting this data. We have, these massive, computers and supercomputers that can process all of this data to come up with a solution. Really over the last, I'm going to say over the last 20 years, weather forecasting, I know it doesn't seem like it sometimes, but weather forecasting, kind of in the 1 to 3 day window, is actually fairly accurate compared to what it was 35, 40 years ago. And a lot of that has to do with just having the computer processing ability to take in all this data and then process all the data and then build a model for the weather and then accurately or fairly accurately predict what's going to happen, 1 to 3 days out. After kind of the 3-5 day window, that's when it gets a little shaky. There's a lot of, each model has a number of assumptions and there's so many different things that can happen. But our weather forecasting has actually gotten really good kind of in that 1 to 3 day period of things.
Just one more thing on wind before we move on. Going back to our very first episode as a podcast. So it sounds quite a bit different than today's episode does because it was early days. But that building, the Citicorp building, the structural engineer for that project realized shortly after it was completed that the structural design would not be able to withstand some of the more extreme winds that were possible. I can't remember exactly what it was. I think it was a 1 in 50 year storm or a 1 in 100 year storm. And so he actually went back in and added some additional stiffeners to the building to make sure that it could withstand those future storms. And that building's still standing today. So it's interesting that our first failure wasn't really a failure, but I thought that was a really important story. He realized his mistakes, owned up to them, and did what it took to correct them. And I think that was really brave of him. And we don't always see that. We see a lot more, at least on the failures we've covered, we see a lot more not believing that the issues are as bad as they think they are, or ignoring people that are trying to wave the flag and point out some of these issues. And so I thought that was a really important story. So if you want to go check that out, it does sound a little different because it is, our first episode as a podcast, but it's number one.
And it is only Nicole talking on that episode.
Yes, that was pre-Brian. Still a really good episode, though. I recorded it, at least 3 or 4 times because it was the first one.
Back to our failure for this episode, though. The Tacoma Narrows Bridge is located in Washington State in the United States of America, and it connects Tacoma, Washington, south of Seattle, with the Kitsap Peninsula across the Puget Sound. So the bridge spans the Tacoma Narrows, or as the locals call it, I believe, just the Narrows, which is a strait that connects the South Basin and Central Basin in the Puget Sound. So a bridge had been proposed in this area since as early as 1889 as a railway trestle bridge, amongst other proposals by Joseph Strauss from the Golden Gate Bridge and David Steinman, who was fired, but later went on to design the Mackinac Bridge in Michigan in 1957. David Steinman apparently predicted the bridge collapse 2 years before it opened. Again, this is, kind of 1940s era, late 30s, early 40s. So I feel that insight, especially if it, he'd kind of written it down and there was some calculations for it, I feel that was probably a little ahead of its time. 2 of the major roadblocks, though, were the cost of the bridge itself and the ferry contract that was running service across the Narrows at the time. Clark Elridge, a Washington State engineer, proposed a tried-and-true conventional bridge design that would cost, at the time, $11 million US, which is over $239 million US today. So I feel that's a fairly expensive bridge, but it is a fairly wide strait, even though it's called the Narrows. So that seems like in the right ballpark. I think $240 million. That seems not unreasonable for this bridge. So the plan included a set of 7.5 meter deep trusses to sit under the roadway and stiffen it. And today, experts believe if this was the bridge that had been built, it would likely still be standing today.
Mosieff claimed he could build the bridge for cheaper, and him and Frederick Leinhard used deflection theory to show that the stiffness of the main cables from suspenders would absorb as much as half of the static wind pressure that would push the structure laterally or sideways back and forth as the wind hit the side of the bridge. The forces would transfer to anchorages and towers, and this design only required 2.5 meter plate girders instead of the 7.5 meter deep trusses, resulting in a more elegant and sleek design and reduced construction costs. And I gotta say, oftentimes in mechanical engineering, we get asked to change things for aesthetic reasons. And I understand, but functionality should trump aesthetics at all costs. To me, at least to me, that's where my brain goes. And so it's just unfortunate here that they chose the quote unquote prettier design that lasted 3 months when the quote unquote uglier design would be still standing today. So food for thought. Mosieff's bridge was estimated to cost about $8 million, so $3 million less than the proposed deep truss design. And that $8 million bridge back then would be worth would have cost about $174 million today. Of that $8 million price tag, about $6 million of it would have been paid for by the Federal Public Works Administration, and the remainder would be collected from tolls. Construction of the bridge took 19 months and came in under budget, which we've talked about before, does not happen anymore. And it ended up only costing $6.4 million US, which is a lot under budget. And again, that just does not happen anymore. I don't know of a project that's come in under budget. It's very rare.
I think I've worked on one project that's come in under budget, and one major project. There's, smaller projects. Sometimes it's easier to come in under budget, but for larger projects that take multiple months, I think I've worked on one of them in 15 years.
And just some background on that, it's not that costs spiral out of control during the project and we don't manage them. It's more that the budgets and the schedules are so tight and so dialed in that there's really no room for contingency, and anything in construction, if anything can go wrong, it will go wrong, and you really do need some type of contingency. And if you have one little thing go a little bit sideways, it just pushes you over budget. So it's not that we're managing jobs worse than we used to, it's that the budgets are so tight nowadays because every single penny is counted when the budget is formed, and there's usually not always a contingency allowed for in that initial budget.
Which there always should be a contingency allowed. That's always been my opinion, that there should be contingency in projects. It's because there will likely be some unknown things that come up in your project, or material costs will be more expensive than what you thought, or delivery costs, or there'll just be additional things that you didn't even account for in your original budget or your original scope of work. So yeah, that usually winds up with a lot of change orders, and like we've seen, or Nicole and I have seen quite a bit, projects that do wind up finishing a little bit later, or quite a bit later than what they were initially scheduled for, and then costing more than what their original budget was allocated for. Just seems to be one of those things that happens nowadays with projects. But I still do my best to accurately give a budget for clients and for projects, but sometimes it just doesn't work out. So the bridge itself was the third longest in the world at the time, after the Golden Gate Bridge and George Washington Bridge in New York. The total length was just over 1,800 meters, and the longest span of the bridge was just over 850 meters. The bridge itself had almost 60 meters of clearance to the water below, but it was fairly narrow compared to the Golden Gate Bridge and was 12 meters wide, providing only 2 lanes for traffic. So it's pretty narrow. So the narrow plate girders unfortunately proved to be the bridge's undoing. The thin girders didn't offer much rigidity, and the bridge moved easily in wind speeds over 54 kilometers per hour, causing alternate halves of the center span to rise and fall a couple meters over 4 to 5 second intervals. The movement was felt through construction and continued after it opened, which is how the bridge got the nickname of Galloping Gertie.
The state and others tried several things to stabilize the bridge, including adding tie-down cables to the plate girders, which were anchored to 50-ton concrete blocks on the shore, but the cables snapped shortly after they were installed, which should have been a major indicator of problems to come. They tried adding a pair of incline cables that ran from the main cable on the bridge deck to the middle of the span, but they were ineffective, although they were still in place at the time the bridge collapsed. And they also tried adding hydraulic buffers that were installed between the towers and the floor system to dampen the longitudinal motion. The seals of the unit buffers were damaged when the bridge was sandblasted before paint, so the damper's effectiveness was pretty much nullified. So that was really silly of them to put something in to help and then just completely void it. Professor Frederick Burt Farquharson created a 1 in 200 scale model of the bridge and a 1 to 20 scale model of the deck to study methods to reduce oscillations. His study was completed on November 2nd, 1940, 2 days before the bridge collapsed, and he recommended 2 solutions. One was to drill holes in the lateral girders along the deck so that air could pass through, and this just reduces the forces of the wind that are being put on the bridge itself, because without those holes, the bridge kind of acts as a sail, and so with those holes there, the wind can pass through and it's not exerting that force on the bridge. This option wasn't chosen because it's irreversible, but you know what else is irreversible? The bridge collapse. His second recommendation was to add fairings or deflector vanes along the deck to make it more aerodynamic, and this option was chosen, but they didn't have a chance to implement it before the collapse.
The main span of the bridge collapsed on the morning of November 7th, 1940, in 64 km per hour winds. The only casualty was a car and a Cocker Spaniel who bit rescuers trying to save him and refused to leave the car even after it fell into the water. The bridge deck had oscillated in a twisting motion that gradually increased until it tore the deck of the bridge apart. So the bridge remnants were found a few weeks later at a depth of 55 meters. They have never been removed, and neither has the car, and it remains an artificial reef. Through a few insurance policies, 80% of the bridge value was collected without incident, but one of the insurance agents pocketed the premiums and was charged with grand larceny. The collapse was filmed by at least 4 people and is still shown to many engineering, architecture, and physics students today, including myself when I was at university 15 years ago, 20 years ago, a long time ago. I've certainly seen footage of this. It's also come up later on just in various other things I've been involved in. We have included one of the many links to the collapse on the webpage for this episode at failurology.ca if you haven't seen it or if you'd like to look at it again. I don't know if it's jarring or graphic, but looking at it, I remember the first time I watched it, I certainly realized that bridges and roads shouldn't have been bending in the way that they were bending in the video, and it was going to lead to bad news bears. And unfortunately, it did lead to a bridge collapse.
Yeah, it's in a really bad way. It's impressive how much the bridge moves and flexes and waves up and down before it just completely collapses. I've certainly never seen anything like that in real life, and it's the most extreme example I can think of this being caught on video. So if you haven't seen it, I do recommend checking it out. Steel and concrete just really shouldn't bend that way, and it's impressive that wind was able to do that. Nature is scary. A commission was formed by the Federal Works Agency to explore 3 possible causes for the collapse. They looked into aerodynamic instability by self-induced vibrations in the structure, eddy formations that might be periodic in nature, and random effects of turbulence, that is, the random fluctuations in the velocity of the wind. The commission report noted 3 key points that led to the failure. They noted that the principal cause of the failure was excessive flexibility, both vertically and in torsion, which is in twisting. They noted that the solid plate girder acted like an airfoil, which created extra drag and lift, which added forces to the bridge that it was not capable of withstanding. And also they noted that aerodynamic forces were little understood, and the bridge should have been tested in a wind tunnel before it was constructed. And that is certainly not the first time we have heard that.
Several factors contributed to the flexibility of the bridge, including the deck being too light, the deck being too shallow, which was a 1 to 350 ratio from the center span, the side spans being too long compared to the length of the span, the cables being anchored too far from the side spans, and the width of the deck was narrow compared to the center span length, which turned out to be a 1 to 72 ratio. The earlier design, with 7.5 meter deep trusses, were open webs that would allow wind to pass through, but the plate girders were solid, forcing air to go around them. The force of the wind on the solid girders caused the bridge to sway and buckle in even mild winds. And to make matters worse, the vibration was transverse, so one half would rise while the other half lowered. Even though these oscillations were there before the bridge even opened, it was thought that the mass of the bridge was enough to keep it together, and unfortunately, that was a very wrong assumption.
On the day of the failure, the wind speed created never before seen twisting motion, and probably never seen since. And that, like we said, caused the 2 halves of the bridge, the 2 halves along the length of the bridge, so one side versus the other side, to twist in the opposite direction, with the center line staying relatively motionless. So it's almost like if you put your arm out straight and you twist your hand back and forth so your palm's facing up and then your palm's facing down. That's kind of what each half of the bridge was doing. This was associated with the slippage of the cable band on the north cable at the midspan, and when that band slipped, the north cable split into 2 segments of uneven length. And this imbalance transferred to the thin plate girders, which twisted easily until the failure occurred. Even though the bridge had issues before and it had lots of movement on it, especially during mild winds and worse in higher speed winds, this was much more extreme than they'd seen before. And so luckily they closed the bridge. They were able to close it well before the collapse happened so that there was no casualties. And aside from the bridge collapsing, the impact was not very widespread. The twisting motion of the bridge was caused by aeroelastic fluttering that did not self-limit, meaning that it continued to grow with each swing. So it's like when you swing on a swing set and every time you go a little bit higher, kind of same idea. On top of that, after some time, the forces of the wind were outweighed by the forces of the bridge swinging back and forth, and eventually the swing was more than the suspension cables could hold, and several of the cables failed. And of course, when the weight of the deck was transferred to the remaining cables, they were overloaded and they broke, causing most of the bridge deck to fall into the water. While this was caused by the wind, it wasn't so much that the wind knocked the bridge over. It was more that the wind got the bridge to swing. And as the swing got a little bit more and a little bit more, the bridge started to just destroy itself. Mosieff visited the bridge a week after the collapse, but was, quote, completely at a loss to explain the collapse. Even though his design pushed the boundaries, it was still within accepted theory at the time. His deflection theory has now been supplemented by aerodynamic analysis to prevent a repeat of the Tacoma Narrows Bridge.
At the time of the collapse, there was almost no recognition amongst bridge engineers at the time that the wind created vertical movement at all. They added stiffening trusses for sideways movement of the cables and roadway from traffic loads and temperature changes, but had no means to accommodate wind or vertical movement. So even though earlier bridges had failed due to the wind, they believed those occurred due to heavy traffic loading and poor workmanship. As well, bridges such as the 1883 Brooklyn Bridge were designed to stabilize against wind stresses. But the perspective at the time the Tacoma Narrows Bridge was built was more on visual preference over structural engineering. The bridge has been studied by many people that are much smarter than us over the years, so we're not going to get into all the different theories about why it collapsed and what could have been done differently, but if you want to, please check out the links on our website at failureology.ca for more info.
The cable anchors, tower pedestals, and most of the substructure that survived the collapse were reused to create a replacement bridge, and that opened in 1950, so 10 years later. The towers themselves shifted 3.7 meters towards the shore as a result of the collapse, and so they unfortunately were dismantled. The replacement bridge exceeded its traffic capacity in the late 90s and early 2000s, and a second parallel bridge was added to carry the eastbound traffic, while the 1950s bridge carries westbound traffic. So if you happen to Google Map it, it'll look like there are two separate bridges. One handles traffic going west, one handles traffic going east. All three bridges, so the 1940, the 1950, and the new bridge that was built in the early 2000s, are all called the Tacoma Narrows Bridge, just to keep it interesting. For future bridges, engineers incorporated aerodynamics into the design, which is very important, and also wind tunnel testing became mandatory, which is, again, very important. In the US, bridges that receive federal funding are required to have their designs subjected to a 3D wind tunnel analysis model, which I think is really important. And while this technology certainly didn't exist in the 1940s, there were scale models of your bridge design that could be made and then tested in an actual wind tunnel which is essentially a cylindrical tunnel that's made and then a fan is blown in one end and they test how the structure reacts. The Bronx Whitestone Bridge, which is a similar design that spans the East River in New York City, was reinforced in 1943 with 4.3 meter steel trusses on both sides, and this was intended to weigh down and stiffen the bridge. In 2013, those trusses were replaced with aerodynamic fiberglass fairings on both sides of the bridge deck.
A December 1st, 1951 windstorm revealed instabilities on the Golden Gate Bridge similar to the Tacoma Narrows Bridge. In 1953 and 1954, lateral and diagonal bracing was installed to connect the lower cords and the two side trusses to stiffen the bridge deck in torsion. Because of the Tacoma Narrows Bridge collapse, suspension bridge designs reverted to the deeper and heavier truss design until box girder bridges were developed in the 1960s. Those had their own issues. Check out episode 22 of this podcast about the Westgate Bridge in Melbourne, Australia for more information about those designs.
I've said this lots before, I'm not a structural engineer, but we have talked about similarities between the Golden Gate Bridge and the Tacoma Narrows Bridge. They were built in the same era. They were built by some of the same people. They followed similar theories, but I think there's a couple key differences. The Golden Gate Bridge is a much longer span, and it's also much wider. So that bridge was 6 lanes total, 3 each way. I think because of the length and the height as well as the width of the bridge, the Golden Gate Bridge is just probably quite a bit heavier than the Tacoma Narrows Bridge. I think Tacoma Narrows being so narrow didn't help it because it didn't have much structure to support itself. It was really long and skinny, and I don't think that helped. So I think that was a key difference. I'm also not sure how much this played a factor, but everyone was watching the Golden Gate Bridge, and it doesn't seem like the Tacoma Narrows got as much attention. And so I wonder if that impacted how much double checking and triple checking was done on the design. I didn't come across anything stating one way or another in research, but That's just something that kind of came to mind for me, that everyone was looking at the Golden Gate Bridge. And so I think it probably was put under a bit more scrutiny than some other bridge designs. So those are just kind of some high level differences, key differences between the two bridges that I think contribute to the fact that the Golden Gate Bridge is still standing and the Tacoma Narrows lasted 3 months. So we've talked about how Mosieff's deflection theory is now supplemented by aerodynamic analysis and wind tunnels. And today there's a lot of modeling software programs that exist to help engineers with complex calculations. I myself use software programs to develop and calculate heating and cooling load calculations or hydraulic calculations or other things. And while there's always a risk with software and you have to double check the results that it gives you, assuming you know how to use the software, it does take out some of the human error because you're not so worried about the math because the program does the math for you as long as all of your inputs are correct. And so there's definitely value for those software programs as engineering and design get more complex. I would guess that most engineers use some type of software, whether it be these modeling programs, online calculators, or even when I'm not using that load calculation software, I use spreadsheets many, many, many times a day. And the reason I like spreadsheets so much is, one, because it takes out simple math errors because the program does it for me, but also it allows me to change variables easily. So if I calculate what I want something to be and then it doesn't quite give me the output that I need or the output that I can make work, I can play around with the variables to see how I can land where I need to be. And I can do that really, really easily with a spreadsheet in a way that I cannot do with a calculator and a paper and pencil. So online software is really helping engineers do their job as long as we know how to use the software and understand its limitations.
So similarly, just like Nicole, I use a ton of spreadsheets a lot of the times for like cost estimating related stuff. Kind of the engineering that I work in, it's not as calculation based as kind of the engineering that Nicole does. So we use some fairly complex kind of custom built software for a lot of the processing and analysis work that we do. But certainly when I go back, the company I work for has been around for 40 plus years. When I look back on some of the things that they were doing in the early 1980s, with some of the very rudimentary CAD software packages, computer aided design software packages, and even some of the manual plotting that they would do of the data that they got from imagery data to build some stereo models, so some 3D height models for things like ski hills or mountain ranges. I'm just impressed that people were able to make the limited data they had work. And then I look at what we have now, and we have millions and millions of data points coming in for projects, and we're able to process and model all those points. Without a lot of that software that we use on a day-to-day basis that I think we take for granted, at least I do some of the time. It makes our job so much easier, but there's also so much more data out there that needs to be integrated into a model. So back in the day, should have Mosieff used a wind tunnel? Probably. I don't know how common wind tunnels were back then for this sort of modeling, or if that was kind of more of a an aviation type use or a car design thing. And we're looking at this also, essentially 80 years from when this happened, probably 85 years from when it was designed or more, and saying what should have been done back in the late 1930s and early 1940s, where we're taking, for granted spreadsheets where we can change one value and it will update, across multiple sheets and multiple tables. So I try to take that into consideration when we look at some of these failures that happen, 60, 50, 80 plus years before we're doing this recording.
Yeah, I would agree. We do probably take software a little bit for granted. It helps us do our job better and faster, but with that comes other challenges, which is that we do more jobs in less time. So, back when this bridge was built, the people who were building it and designing it probably worked on only this bridge for several years. And that just isn't necessarily the case. Maybe in structural engineering, when you're working on a large bridge, that is the case. But even in mechanical engineering, in my line of work, even when we have a large project, even if it's multiple towers, yes, that project may go on for 5 or 6 years, but I'm not working on only that project. I'm working on that project and several other projects at the same time. So the software has helped us in that we can do our job better and faster, but now we have to do more things at once, which, lucky for me, I am very good at multitasking, or as we call it now, task switching. And I'm very good at moving from one task to another quickly, which is not something that everyone is good at. So that it works for me, but I can see how that would be difficult.
So there you have it, the Tacoma Narrows Bridge collapse. Even though the bridge collapsed 3 months after opening, it has been studied by engineers, physicists, and mathematicians for decades.
For photos, sources, and an episode summary for this week's episode, head to failurology.ca. If you're enjoying what you're hearing, please rate, review, and subscribe to Failurology so more people can find us. If you want to chat with us, our Twitter handle is @Failurology. You can email us at thefailurologypodcast@gmail.com. You can connect with us on LinkedIn, or you can message us on our Patreon page. Check out the show notes for links to all of these. And thanks to everyone for listening. Tune into the next episode where we'll talk about the Mount Polley Tailings Dam failure near Williams Lake, British Columbia. Bye, everyone. Talk soon.